Hi everyone, welcome to another ZX seminar. Today we have Dichuan and Gao. We'll be talking about the Galois-qudit ZH calculus and quantum Reed-Solomon codes. Please, Dichuan.
All right, thank you. Um, so I should probably start by apologizing because I am currently a bit sick, so my voice is not the clearest. So please stop me at any point if like you couldn't hear anything clearly or if you just have any questions in general. No need to wait until the end. Yeah, so this project is kind of a group project in the quantum group in Oxford. Um, some contributors also work at Quantinuum. Um, so maybe I'll start by going through what I want to cover in this talk. Um, so I'll start with some background on the qubit ZH calculus, the ZH calculus that probably a lot of people in this group are already familiar with. And then I'll give some background on Galois theory, just to give you a sense of what this notion of Galois qudits is all about. And it's a very useful concept for error correction in general. Um, So then I will go on to talking about this ZH calculus for Galois qudits that I'm developing. So I'll define the calculus. I will show you how the field arithmetics of Galois fields work in ZH calculus. And then I'll go on to talk a little bit about the universality of this ZH calculus. And then in the last section of the talk, I want to show you what we can do in terms of error correction in the ZH calculus. So I'll show you how the Pauli groups work, um, how you can work with Paulis, pushing them through spiders and so on. Um, and then I will give an example of a CSS code, which is called the Reed-Solomon code, which has a particular affinity to the ZH calculus. Okay, so if that sounds good, let me start with the ZH calculus as we're familiar with it right now. So in qubits, the ZH calculus has two families of generators. You have the Z spiders, which are just the same as your ZX calculus Z spiders. And then you have this H spider, which is really just a generalized Hadamard gate. So the formula in here, you can see if there's one input and one output, then this is just a Hadamard gate. But then it's simply generalized to more inputs and outputs. Now, we really like the ZH calculus for many reasons. But one of these reasons that's important to me is that it's easy to implement a quantum AND gate. So when I say a quantum AND gate, I mean a gate that operates on the computational basis as the logical AND. So we can think of it this way. Um, and this is so this corresponds to a classical function, which is not linear in F2. Uh, and this is particularly useful because that allows us to implement the Pauli gate in my ZH calculus with much more ease than what we can do in the ZX calculus directly. So here, this diagram on the left over here, this diagram is the Pauli gate. So it toggles the third qubit if and only if the first two qubits, I and j, are both 1. Um, so we would really like something that works like this in qudits. And by the way, the reason why we care about the Pauli gate is, of course, it's by itself a universal gate set. Okay, so there are indeed existing generalizations of the ZH calculus to qudits. So first in 2023, Patrick Roy and friends in his master's dissertation, I think, published this generalization to prime dimensional systems. So these are now Hilbert spaces whose dimension is a prime number. And what he's done is, if you look at the coefficients inside this formula, the base is was originally -1. Now it's replaced by a p-th root of unity. And then the rest of the structure is just the same. So what this gives us is if you write out the same diagram as here, if it's just take this diagram, but draw it out in this new qpit ZH calculus, then you get multiplication in FP. So FP, if you're not familiar with this notation, that's just the cyclic ring Z mod PZ. So it's like it's addition and multiplication defined modulo P. Then you can just take this one step further. Neil de Beaudrap and East in 2023 defined a general qudit ZH calculus, where now, okay, instead of -1 inside here, you have omega, which is a d-th root of unity, where d doesn't have to be prime. And so then what you get in this calculus is the AND gate becomes cyclic ring multiplication in Z mod DZ. Okay, so in this calculus, what we'll see is that it kind of corresponds to the system in which the Pauli group is the Heisenberg-Weil group. But what we would be interested in is actually looking at something slightly different for non-prime dimensions. So one thing you can see is if D is not prime, then multiplication in this ring is not invertible. For example, if D is 6, then 2 times 3 is 6, which is 0 in my ring. But 2 and 3, neither 2 nor 3 are 0. So multiplication by 2 or 3 are not invertible. The question is there a non-prime system in which multiplication is invertible? And the answer is there is. So for any q, which is a power of a prime, we know that there exists a finite field fq of size q. And so when t is not 1, in other words, when q is not prime, then this field fq is not isomorphic to the cyclic ring. And such a field is called a Galois field. So Galois theory is a theory that people generally use to understand such fields. And what we would really like is to find a ZH calculus for prime power dimensions such that the AND gate, the same diagram as we had before for the AND gate, now means field multiplication in the Galois field. So why do we care about this? Well, I think it's mathematically pleasing, but also this is very useful for particular strategies in error correction, which we'll see later. So now let's go on to quickly sketching Galois theory. Yeah, please stop me, anyone with any questions in the middle of my talk. Okay, so Galois theory, usually I think the first example that people give is the case where P and T are both 2. So what we're looking at is a field of size 4. Oh, I should have said this way earlier, but there's this unfortunate overloading of the word field. When I say field, I'm not talking about the field of quantum field theory. I'm talking about like an algebraic field, as in a set in which multiplication is invertible. Okay, so we're looking at the field of size 4. It has 4 elements, which I will call 0, 1, alpha, and alpha plus 1. So these 4 elements are closed under addition in the obvious way. So if you add 1 to itself, you get 0. If you add 1 to alpha, you get alpha plus 1, and so on. And they satisfy the following multiplication table. Now, if you stare at this multiplication table for a second, what's really happening here is this bit of the table is like a Sudoku, meaning that each row mentions each non-zero element exactly once, and each column mentions each non-zero element exactly once. And so that is what makes multiplication here invertible. Some other ways to think about this, just to give you some intuition, is you can think of alpha as an abstract symbol for a root to this polynomial here, this polynomial f. So this is a polynomial whose coefficients come from f2, right? Every coefficient is either 0 or 1, but it doesn't have a root in f2, because whether you plug in x equals to 0 or x equals to 1, you obtain the output 1. So now what you do is you adjoin to f2 an abstract symbol alpha, which is just the root for this polynomial, just like how I is an abstract symbol for the root to x squared plus 1. And so then you obtain f4 as a quotient of this polynomial ring. Okay, so that's one way to think about this, to think about what alpha is. So alpha is not really a number in the usual sense. It's a symbol for a root. Another way to think about f4 is it's a two-dimensional vector space over f2. And a basis for this two-dimensional vector space would be 1 alpha. And you can see, okay, so each of these 4 elements are really just like a length 2 vector where each entry is either 0 or 1. And algebraists would say that f4 is a degree 2 field extension over f2, and alpha is a generating element. Okay, so that's the example. Now let's talk in generality. So, sorry, what did someone want?
What's alpha plus alpha?
Oh yes, that's a very good point. So in f4, everything has characteristic 2. So alpha plus alpha is 0, as is anything plus itself. Yeah. Okay. So in general, if t is any natural number and p is any prime number, q is p to the t, then we have a finite field fq of size q, and it's a t-dimensional extension over the prime field fp. So remember, the prime field is just the cyclic ring we're familiar with, and a t-dimensional extension just means fq has the structure of a vector space over fp. And in particular, this means that fp is in fq, or maybe another way to say is there's a copy of fp in fq. So this is namely this bit here. Okay, and we know that every finite field is of this form. So if you have a finite set for which you can define multiplication and addition such that multiplication is invertible, then it is of this form. It's a prime power field. And yeah, we said before, when t is not 1, then fq is not a cyclic ring, and it has characteristic p. Okay. On this finite field, we can define some simple machineries for doing Galois theory. So we begin by defining the Galois group, which is just a group of field automorphisms of this finite field. So fq has t distinct automorphisms, and these are all given in this form. It sends an element to x to the p to the tau, where tau is ranging between 0 and t minus 1. And this is indeed a group, because if you set tau to t, that's the same as setting tau to 0. And an interesting thing is that an element of the big field fq is stabilized by this group of automorphisms if and only if it's actually within the smaller field fp. It's actually within the prime field. And we call an element normal if its orbit under the Galois group is a basis of fq. So you can think of it like in a weird way as it's sort of normal to this fp contained within fq. So it's like maximally not in fp. So its orbit like this, consisting of these elements, forms a basis for fp forms a basis for FQ over FP. So in other words, every element Y in the big field can be expressed uniquely as a weighted sum of such things. Right. So the other thing we can do with these Galois automorphisms is we can sum over them. So we define the following linear map where you take any field element J and you apply every possible Galois automorphism to it, and then you sum over all the outputs. And this gives us a linear map, which is from FQ to FP. To see that the outputs of this linear map are always in FP, you just have to try to apply another Galois automorphism to it. Like imagine if you were to apply another Galois automorphism like this. Okay, so then this distributes in, and then you see that you've just permuted the terms in your sum. And so this map actually gives you something that's stabilized by the Galois group, and therefore it gives you something in a prime field. And this map has many nice properties. One is surjective for finite fields. It's called the field trace because it measures the linear algebraic trace of this linear operation, which is just defined by multiplying by J. So multiplying by J is a linear map from FQ to itself. And so it has a trace, and this is precisely the thing that gives you that trace. But it's really important not to confuse this with a trace of a linear operator over the Hilbert space of qudits, because the field FQ, that's going to be our computational basis. So this trace function is an algebraic structure within my computational basis. Okay. I promised the last bit of Galois theory before we go on to quantum stuff. Is this notion of a primitive element. So the word primitive is like notoriously overused in algebra. But in this case, what I mean by primitive is, okay, you take the multiplicative group of all the non-zero elements of FQ. Okay, so all the non-zero elements of FQ, multiplication by each of them is invertible, so they form a multiplicative group, and a result of Fermat's little theorem is that this multiplicative group is cyclic of size q minus 1. And so it has, because it's cyclic, you can find generators for it, generating elements for it, and an element that is a generating element in this sense is called primitive. So if psi is primitive, then the group of non-zero elements is of this form. Okay, so now a useful theorem for us is for any Galois field FQ, you can find an element psi such that it is primitive, it is normal, meaning that its images under its orbit under the Galois group forms a basis, and finally its field trace is 1. Okay, so any questions so far about the algebra before we go on to graphic stuff?
Dichuan, this property with normal, is this essentially a permutation? No, what you had on this slide, you don't have to switch.
Oh yeah.
Slide. Is that essentially a permutation of the set above it? Like, does this like p to the power of 0, p to the power of 1, p to the power of 2? Does that sort of give you the elements that you see above in the primitive definition?
Yeah, that's a great question. So this set has size q minus 1, so it's all the powers of psi. But then this set has size p, so it's the powers of psi where the exponent is itself a power of p. And so this is why this forms a basis of your big field, whereas this kind of just literally traverses the entire big field.
And then I think is the way that I should think about this, the set with a normal property that like something to the power of p, like since you're doing modulo something like to the power of t, actually this is a smaller power. If I take a p to a large power, then actually this sort of, by the definition of being a polynomial ring, this sort of goes down to a lower level.
Yes, exactly. Because the reason is the map that sends x to the map that sends x to the q. Remember, q is p to the t. So this map is actually just identity in FQ. I mean, some people define FQ this way, like the field of all the roots of this polynomial xq minus x. Yes, so that's why once you get to a high enough power of p, then you've wrapped back to identity.
Okay, thanks.
Okay, so that's all about Galois fields. So now we can actually define the ZH calculus here. So I will define the ZH calculus in the phaseless case first, having three families of generators. So first you have the Z spiders, which we're used to. Then you have the H spiders. So now what's happening in the H spiders is these coefficients, I'm going to take the base, this omega, as a pth root of unity, not a qth root, but a pth root of unity. And then in the exponent, I'm going to take the field trace of the product of all the inputs and outputs. So, I mean, one thought exercise you can do is, okay, what happens if I forget about the field trace? Well, if I forget about the field trace, then you take the product of all the inputs and outputs. Well, these are coming from the Galois field, so they're not really even numbers. So it wouldn't really make any sense to raise a complex number to that power at all. So, okay, you take the field trace, now you get something in the prime field, then you raise a pth root of unity to that power. So everything sort of just nicely irons out. And this is what gives us the ability to do field arithmetics here. Then the cost of that is I needed to add a third family of generators, which really only consists of one single diagram, which I'm calling the psi lollipop. And this corresponds to an element of the computational basis, which in the Galois field is a primitive element, normal, and trace one, which is guaranteed to exist because of the previous theorem. So this is my calculus. As before, as in the qubit case, you can introduce phases to it, or labels to the H spiders by simply replacing that pth root of unity omega with any complex number whatsoever. Okay, so that's the definition of the calculus. You can, yes, Neil?
I wondered whether that psi generator is in some sense playing a similar role as a degree one not dot.
A degree one not dot.
In the ZH calculus, where you've there's a syntactic sugar, so that it's a derived generator in the original presentation of the ZH calculus, but something that essentially ends up playing the role of a generator that's proportional to ket1. There's some issue, I suppose, with scalar factors. And then when you merge this with a gray dot, there will be some sort of fusion-like rule. Then you get something that is syntactic sugar used to represent negating what's happening on the bits on the index. I wonder whether this psi is playing a similar role here.
Yes. So it is. The thing about Galois fields is that the role of one is kind of split between two different things. So first there's the one, which is the multiplicative identity. And this in our calculus, is going to look like this, very similar to the usual ZH calculus stuff we're used to. But then the other role of one, which is having field trace one, this role is given to this psi. And in fact, in Galois fields, the field trace of the multiplicative identity one is going to be t. So when t is one, of course, they're all the same thing. But when t is not one, then yeah.
Okay, thanks.
Yeah. Right. So we can still have the usual syntactic sugars of the ZH calculus by defining the X spider, just conjugating the Z spider with, well, not conjugating, that's not quite right, but like wrapping it around with H gates. We have some real scalars defined this way. We'll also have access to complex scalars, which you'll see a little bit later. So that's the calculus. Now, as promised, we need to be able to do field arithmetics in the ZH calculus. And indeed, we have that. So in my calculus, if you have one in, one out X spider, that is the same as having two H gates in a row, and that is the same as taking the negative in your computational basis field. If you have a 2 in 1 out X spider followed by a 1 in 1 out X spider, this is the same as field addition, and its corresponding identity is this. If you have a 2 in 1 out H spider followed by the adjoint of an H spider, that is the same as field multiplication, and its corresponding identity is here. I should quickly mention here that the H spider is no longer self-adjoint, simply because we've introduced complex matrix entries. Okay. So that's the field arithmetics. So that already gives us access to pretty much all of Galois theory. So the Galois group acts on the computational basis. So you can think of this Hilbert space as a group representation of the Galois group. And this group figures in our graphical calculus as these maps. So whenever you see like a gadget like this, that's just raising something to some power. And therefore, you can implement the field trace as this diagram right here. So actually, yes, let me talk quickly about this blue box I have here, which I think people call the annotated bang box. I'm not sure if that's how you pronounce it, but yes. So what is it doing here? Well, it's really just a shorthand for copying a diagram several times according to the annotation, and then connecting it in the right way to the diagrams in its context. So it's really just a shorthand for this operation so that I can avoid writing ... everywhere. Yes, so if we go back to this diagram here, what it's doing is it's raising your input to all the powers, which are themselves powers of P, and then summing at the end using some X spiders. So that acts on a computational basis as the field trace. And I've noticed that this map is very much not self-conjugate, no, what am I trying to say? It's not self-transpose. It goes from the big field to the small field. So that's why I've introduced this asymmetry. Yeah. Okay. So we have all the field arithmetics. Now I want to talk quickly about universality, unless people have questions about the arithmetic so far. Okay, so then with universality, first we at least need to have every computational basis state in our graphical calculus. And that is not as obvious in this case as in the case of, for example, Neal's calculus. Because in our case, basically, if you start with the computational basis element corresponding to 0, and you keep adding 1 to it, you only get the first P elements in FQ, because FQ is characteristic P. So we need a better way to get all the basis elements, and luckily we do have that. So first we start with 0, and 0 is fine because we already know that this is the additive identity. Then for any non-zero j, we use the fact that psi is primitive, so that we know that some power of psi, we can raise psi to any power using this diagram, is going to give you the computational basis j. So, okay, we do have all the computational basis elements. So that allows us to just use the shorthand where an X lollipop labeled by J for arbitrary J in FQ, it's just going to be this state. And then a Z spider labeled with J will just be defined as the same X spider, but transformed by a Hadamard. And these lollipops will satisfy what we usually expect for a pair of Fourier bases. Well, Fourier here means that the scalars are this little thing here. Quick thing to note is that the Z lollipops are not self-conjugate. So the adjoint of a Z I lollipop is actually the minus I lollipop going in the other direction. Okay, so we have the basis states. So then the theorem is that my phased ZH calculus is universal, meaning that for any linear map between several qudits of dimension q, there exists a diagram in my calculus that represents that linear map. I might have to go through this proof very, very sketchily, but the idea is essentially I'm going to reduce the question of constructing any matrix. I will reduce it first to the question of constructing pseudo-binary matrices. Pseudo-binary just means that a matrix whose entries are either 1 or R for some fixed R. Then I'm going to reduce that question to the question of constructing maps that act on the computational basis as a polynomial. You can think of the polynomial essentially as a kind of generalized propositional formula telling you which entries in the matrix are 1 and which entries are 0 are R. And so then you've essentially reduced the question to constructing any classical polynomial function on the Galois field. And you can indeed build any polynomial using a recursive normal form like here. And I think you can probably already guess what this would look like even before I flip the page, since polynomials only involve multiplication and addition. So that's the idea of universality. But the conclusion is any linear map can be constructed in the phased finite field ZH calculus. I am working on a version of this which says that any linear map satisfying certain constraints can also be constructed in the phaseless finite field ZH calculus, but that one is still in the works. Okay, so now I want to take some time to talk about error correction in my calculus. So I should probably start by saying what the Pauli group in Galois-qudits are. So I follow Gottesman in defining the Pauli group like so. If Q is a prime power, then you have these gates. And these gates will take abstract exponents. These exponents are abstract exponents coming from the big field F cubed. So they don't just take numeric exponents. And you just define them like so. So you can see indeed if kappa is 1, for example, then this is just the regular X and Z gates.
Sorry, Dichuan.
Yeah.
When you say abstract exponent, like should I think of this as a map that goes from the FQ to this unitary space? Like for every element of Q, I have a unitary, like another call X and Z. So like X is a function of kappa and Z is a function of kappa. Such that if I apply X of kappa 1 and then X of kappa 2, this is equal to X of kappa 1 plus 2. Like this is kind of like a linear map.
Yeah, exactly.
Okay, yeah, that makes sense.
Oh, Neil, did that also answer your question?
No, well, I was going to interject if that might have been helpful, but I didn't think it was necessary.
Okay. Cool. So from there, you can define the one qudit Pauli group as usual. So you just take the products of these Pauli gates, and the Pauli gates here still commute up to a scalar. So so this set is indeed closed under composition. Then you can construct your n-qudit Pauli groups as usual, just by taking the tensor products of your one qudit Paulis. And so this now forms. I think the phrase Gottesman used was a nice error basis. So it has all the nice properties that we want the Pauli group to have in the qubit case. So they all translate over to the qudit case. Okay, so that is the Pauli group. So obviously the question is, how do we construct these x to the kappa and z to the kappa gates in the ZH calculus? So we can do this fairly nicely like so. So I introduce the following syntactic sugar, where if you take a many-legged Z or X spider, and then attach to it one of those lollipop states that we defined earlier. So here kappa is any Galois field element. Then I will just shorthand it as a Z or X spider with kappa labeled on it. These are basically the same thing as the ZX spiders with pi labels on them, or integer multiples of pi labels on them. So these satisfy some nice rewrite rules, which you can prove in the Galois-qudit ZH calculus. They're basically the same rules as the ones you expect from ZX. So you have color change on the left here. You have spider fusion in the middle here. You have, okay, so this is new. This is if you wrap a classically labeled spider with non-labeled X gates on every leg, that's the same as flipping the sign of your label. And then finally, you have a generalized strong complementarity in this form, where the label on your Z spiders flip, and then your scalar comes in this form over here. Okay, yeah, one thing to note that because in order to define our calculus in a flexometric way, one consequence of that is the fusion of these X spiders is only up to these dualizers. So you need to have these little things on every shared leg between your X spiders. Okay, so these are the classically labeled spiders. And with these...
I have a question.
Yeah.
So with this case spiders, why is there a particular reason that you're adding like an identity spider here, like when you define it?
Adding
like in the previous slides. Yeah, for the right spider. Yes, here.
Oh, I see. Oh yeah, this is not identity. So this is negation. So if you look at, so this bit here is the same as an X lollipop with minus kappa label. I guess another way to think about this is whenever something, whether it's an X spider or a Z spider, whenever something interacts with an X spider, it kind of, the sign flips. So yeah, I mean, so you can see this in the strong complementarity here, for example. So if you were to yeah, I don't think so. If I were to just remove this, if I were to define my classically labeled spiders this way, I don't think the fusion rules would work in any meaningful sense. Neil, did you have an idea on this?
Yeah, if I were to interject, it's as you said, it's basically a consequence of the fact that the degree 2 grade dot in this case is a dualizer, and that is itself a result of the fact, as you said, that you want to get flex symmetry. So this is something that you also see in my calculus, and the reason why you see my calculus with Richard, the reason why you see it in my calculus with Richard is because you also see it in the calculus of Booth and Carrette, who found that you needed to do this to get flex symmetry. So
Yes,
this is just something that you'll tend to see in X-like spiders in higher dimensional flex symmetric calculi.
Thank you.
Cool. Right. I should probably start going a bit faster, but okay. So from these definitions, it's relatively easy to see that your one in, one out classically labeled spiders correspond precisely to the Pauli gates. So you have these semantic mappings here. And using strong complementarity, you immediately get the commutation relation between the Paulis here. So, okay, we have the Pauli gates. Now, what can we do with them in the ZH calculus? Well, they interact with the Cliffords the same way we expect, more or less. So you can so if you have a Pauli on one leg of a non-labeled many-legged X spider, then it kind of just flows through it. Whereas if you have a Pauli on one leg of a spider which is the opposite color to it, then it kind of copies through it. With the provision that whenever something is interacting with an X spider, the sign flips. So this is, you can see that in both this case over here and this case over here. And then the Hadamard gate is still the color change. So if you have a Z spider, if you have a Z Pauli on the left of the Hadamard, that's the same as having an X Pauli on the right of the Hadamard, and vice versa, up to a sign change over here. Now, because we're working in the ZH calculus, we might also want to know how these Paulis interact with H spiders more in general. So H spiders in general, of more than two legs, are not Cliffords, and so we wouldn't expect the Paulis to push through them. However, in a special case where you have an X Pauli next to a many-legged H spider, that is actually the same as having this on the right-hand side, this kind of generalized phase gadget attached to all of the other legs of your H spider. So what is this phase gadget here? What it's doing is kind of, in the ZX calculus, we're used to having a phase gadget where the exponent of the phase is basically the XOR of all the legs that the gadget is attached to. But here, instead of the XOR, it's actually the AND, or the field product of all the legs it's attached to. But it is a phase gadget in that sense. And so you can push an Pauli X through an H spider to get a phase gadget. What we can do with this, I'm not sure yet. So if anyone has any idea, please let me know. Okay, we can also define Pauli boxes in more or less the same way as in ZX. So if you define these diagrams like so, then they have the nice property that if you give the vertical wire, which I'm calling the control wire, a Z lollipop input, then we obtain the corresponding Pauli operator with that exponent. And if you give it an X lollipop input, then we obtain a projector. But now we have to be a bit careful about what these projectors are doing, because they're not really Pauli projectors in the usual sense. So if you look at the diagram here, you can see that it's a rank 1 projector. Now, what is this one-dimensional subspace projecting onto? It is an eigenvector of my Z Pauli. But the operators x and z on my q-dimensional Hilbert space, they only have p distinct eigenvalues. And these p eigenvalues are the phases, powers of my p-th root of unity. And so each eigenvalue has an eigenspace of dimension p to the t minus 1. And so, for example, in the case of the Pauli Z, the eigenspace corresponding to this eigenvalue here is spanned by all the computational basis states whose field trace is theta. And remember, field trace is a surjective function. And so to get the projector onto an entire eigenspace for a fixed eigenvalue, you actually need to do this with your Pauli boxes. So you apply to your control sort of the adjoint of the field trace map, which we defined earlier. Okay, so that's the Pauli boxes. We can construct with the ZH calculus the quantum Reed-Solomon code. I won't go into too much detail with this, but the Reed-Solomon code is essentially kind of CSS code constructed from a classical code which acts on your logical bits as interpreting them as the coefficients of a polynomial. So all the operations involved in the Reed-Solomon code are arithmetic operations. And this only really works in Galois fields, and it's known to saturate the quantum singleton bound. So it is a maximal distance separable code. We can construct the encoder of my quantum Reed-Solomon code by defining this gadget here, which I'm calling the Vandermonde box. What it's really doing is it's really just evaluating a one variable polynomial. And we can just construct the encoder by repeating this Vandermonde box several times. The elements of this encoder interact with the Paulis graphically like so. So we are allowed to push Paulis through it in special circumstances. And so here's an example. If you have a Reed-Solomon code with parameters 5, 3, 1, that means you have one logical qudit. It's being copied and sent to 5 separate Vandermonde boxes. And so in each Vandermonde box, some polynomial computation is happening. Then you get back 5 separate values of the same polynomial. So yeah, this is just an example of how we can use the ZH calculus to represent the encoder of this code. Okay, so I will wrap up here. So what we've done is we've made a qudit ZH calculus for systems of prime power dimensions. It implements finite field arithmetics. It is universal, and it can be used to reason about qudit error correction, especially in the case of Reed-Solomon codes, where there's a special affinity because of the naturalness of polynomials in the ZH calculus. Some things we would like to do is we would like to graphically grok, in Alex's terminology, the stabilizers and logical operators of the Reed-Solomon code. We would like to see how fault tolerance works in quantum Reed-Solomon codes. So what are the transversal gates and so on. And separately, we would also really like to find a complete set of rewrite rules for the Galois-qudit ZH calculus. And that's been in the works for a while. We actually currently don't even have a complete set of rules for the prime qudit ZH calculus. So that would be something that's really interesting for us. Yes, okay, that's all. Thank you.
All right, thank you, Dichuan, for the very nice talk. As people already know how to do clapping in Zoom using the emojis. Do we have any questions in the audience? All right, I see David Phillips raising their hand physically.
Yes, I have a question about your last slide, the Reed-Solomon code. What are the parameters of this? Like 531? Isn't it 513? I'm confused by that.
Yeah, sorry. Yeah, I didn't have time to go through this. So these are not the usual parameters. So this is the notation Gottesman uses. I'm not exactly sure why he uses this notation, but so Reed-Solomon codes are identified by a triplet parameter, where the first entry is the number of physical qudits. The last entry is the number of logical qudits. And the middle entry is kind of the degree of the polynomials used in your encoder. One way to think about this is it is a CSS code, right? So it kind of corresponds to you can think of it as having like C1 and C2. So C1 wait, how do I put this? Yeah, so K2 wait, so how do I put this? K2, okay. Graphically, you can see this here. So K2 is 1, means that there's one logical qubit. Now here K1 is 3, which means that there are 3 Z spiders here, right? So like the other 2 are basically just logical qubits that are being summed over all possible values. I don't remember what you call this. Like this is like a general construction for CSS codes from classical codes. And then 5 just means there are 5 outputs in total.
Okay, thank you.
Sorry, I don't know if that answered the question.
It does.
So Dichuan, if here I replace all the Van der Monde matrices by just X spider, this would be a standard CSS normal form for like qubit Clifford ZX or face tree ZX.
Yes.
Is there like a meaningful sense in which these Van der Monde matrices can reduce to just an X spider? In like say the prime dimensional case?
Not in the prime dimensional case, but when your dimension is just 2, I do think they reduce to the Z spider. Essentially because when Q is 2, when you constructed Van der Monde matrix, this bit right here will just be the identity if U is 1 and disconnects if U is 2. I think. Or it might be the other way around, but yeah.
Also in the general case, when you have this H box thing, if you plug in some specific alpha, it becomes a multiplier. So if you expand the Van der Waals box by plugging in some specific alpha, it becomes the ZX normal form for CSS code with multipliers in between.
Oh yeah, right. That's a much nicer way to think about this. Yes. So each of these things inside the bang box here is essentially a multiplier. And so if you are working in qubits, then the only meaningful multipliers are 0 and 1.
Then a generic CSS code, I guess. So in 2D, each of those boxes you could say is just picking out a subset, I guess, of all the logical bits and the stabilizers to plug into that spider. And here you're saying it's a more complicated configuration of multipliers, which always comes from this matrix. Is that right?
Yep, exactly. Yeah. And the only thing that makes that sort of narrows it down is the fact that each row in this matrix are the powers of a single fixed field element, rather than just arbitrary field elements. And of course, that's also the reason why we know how to push Paulis through them. Is we know that you can just change the phases in your Paulis by the powers of this fixed field element.
In what sense is this a CSS code? Does it sort of give you the X type operators separately from the Z type operators, or what?
It should. I haven't thought about this carefully enough, but Gottesman says this is a CSS code because obviously it has the form of a CSS code.
Okay.
I think one way to think about this is if you were to take the classical encoder of the classical Reed-Solomon codes, you wouldn't have these summations, right? You would just be able to get all K1 logical qudits. And your encoder is just sort of applying these polynomials to them. And then here it's just doing that twice. So your C1 is given by these polynomials, and then your C2 is like orthogonal to this other set of polynomials. Yeah. I know that was very rambly. Let me think about that more.
So in the qubit case, when you have you can make the Pauli box of a tensor product of Paulis by connecting the control wires of the Pauli boxes together using an X spider. Does something similar work in this setting?
Oh yes, it does. It does. Oh right, I forgot to show that. Where did it go? Yeah, I mean, so what you do is you would connect them by an X spider, except on this outgoing control wire that finally touches your input, you're gonna have another X spider. So it will look something like, so you would have a bunch of these, you would join them together with an X spider, and then you're gonna have another X spider. So, and then this is your joining. So that way when you have a kappa here, this Z spider is gonna copy through without having its sign flipped by virtue of this extra X spider out here, and then it will give you what you want. And similarly, now if you plug in the X spider into that thing I was describing, then it fuses in without having its sign flipped, and everything works as expected. What I would like to think a bit more carefully about is how your projector onto the stabilized subspace should be depicted, because here we have yeah, I mean here we have you know, for a single Pauli, the projector onto the stabilized subspace involves this field trace gadget So merging those might be a bit more tricky. I don't see it yet.